What specific problem does the compositional GSM method aim to solve, and how does it challenge the existing assumptions about the capabilities of large language models in mathematics?
The compositional GSM method aims to address the limitations of large language models, LLMs, in solving chained mathematical problems, specifically by evaluating their ability to combine learned concepts to solve new problems. This method challenges the existing assumption that LLMs have mastered grade school math by revealing a significant reasoning gap between their performance on standard GSM 8K problems and the more complex compositional tasks. The study shows that while LLMs can solve individual grade school math problems effectively, they struggle with compositional queries where the answer to one question serves as a variable in another, indicating a reliance on superficial pattern recognition rather than true conceptual understanding. The findings suggest that even high-performing models exhibit brittleness in reasoning, particularly in cost-efficient and smaller models, undermining their reliability in practical applications. Overall, compositional GSM serves as a critical tool for reassessing how we evaluate the reasoning abilities of LLMs in mathematics.
How does the proposed method of compositional GSM work? Illustrate the step-by-step process of how a question is constructed and solved using this approach.
The proposed method of compositional GSM constructs questions by chaining two test questions together, where the answer to the first question, question 1, serves as a variable in the second question, question 2. Specifically, from a subset of 1,200 examples of the original GSM 8K test set, a number in question 2 is modified and replaced with the answer from question 1 denoted as x. The design ensures that the final answer of question 2 is a positive integer that differs from its original answer, maintaining similar magnitude distributions between the original and compositional questions. To ensure logical coherence, 16 candidate solutions for each modified question are generated, and only those with at least 4 agreeing with the expected final answer are retained. The final answer for question2 is then obtained by substituting x and solving the modified question, allowing for a systematic evaluation of the LLM's reasoning capabilities.
Can you provide a simple illustrative example of a compositional GSM problem? Walk through the example to explain how the answer to the first question is used in the second question.
An illustrative example of a compositional GSM problem involves two questions where the answer to the first question serves as a variable in the second. For instance, consider question 1. If there are 5 apples and you buy 3 more, how many apples do you have? The answer to this question is 8 apples. In question 2, we might ask, if you give away X apples, how many apples do you have left? Here, X is replaced with the answer from question 1. So the second question becomes, if you give away 8 apples, how many apples do you have left? The final answer to question 2 would be 0 apples. This structure demonstrates how the answer from the first question is directly utilized in the second question, showcasing the compositional reasoning required to solve the problem.
What are the theoretical or practical benefits of using compositional GSM over traditional benchmarks like GSM 8K?
The theoretical benefits of using compositional GSM over traditional benchmarks like GSM 8K include a deeper evaluation of LLM's reasoning abilities, as it requires models to combine learned concepts from two interconnected questions, thereby probing their understanding beyond mere pattern recognition. Practically, compositional GSM reveals significant reasoning gaps in LLMs that may not be apparent in standard benchmarks, highlighting their limitations in solving more complex chained problems. This is particularly evident as many models perform well on GSM 8K, but exhibit a 2 to 12 times worse reasoning gap on compositional GSM, indicating that high scores on traditional benchmarks can obscure underlying reasoning flaws. Additionally, the study emphasizes the need for a reassessment of how LLMs are evaluated, suggesting that compositional tasks can provide insights into their generalization capabilities and potential overfitting issues. Overall, compositional GSM serves as a more rigorous test of LLM's mathematical reasoning and their ability to apply learned knowledge in novel contexts.
How was the performance of the LLMs on compositional GSM validated or tested? What datasets and metrics were used to measure their capabilities?
The performance of the LLMs on compositional GSM was validated by benchmarking their accuracy on a newly introduced test set, compositional GSM, which consists of two-part questions derived from the original GSM 8K dataset. Each question in compositional GSM requires the answer from the first question to be used as a variable in the second question, allowing for a direct comparison of individual question performance versus compositional reasoning. The accuracy of the models on the compositional split was measured against their performance on the original GSM 8K test set, with the expectation that a model's accuracy on the compositional split should be the product of its accuracies on the individual questions. Metrics used to evaluate their capabilities included the compositional reasoning gap score, which highlights the difference in performance between the two types of questions. Additionally, the study analyzed the impact of instruction tuning and the effects of using code generation versus natural language solutions on the model's performance.
What significant results were achieved in the study regarding the reasoning capabilities of various LLMs on compositional GSM compared to GSM 8K?
The study revealed a significant reasoning gap between the performance of various large language models, LLMs, on the standard GSM 8K benchmark and the newly introduced compositional GSM. Most models demonstrated a clear decline in performance when faced with compositional problems, indicating that while they excel at individual grade school math questions, they struggle to combine learned concepts effectively. For instance, smaller and cost-efficient models exhibited a 2 to 12 times worse reasoning gap on compositional GSM compared to their performance on GSM 8K. Additionally, math-specialized LLMs, despite their extensive training on mathematical domains, showed similar reasoning gaps, with some achieving over 80% accuracy on more challenging math problems, but solving less than 60% of compositional grade school math problems. These findings underscore the need to reassess the evaluation strategies for LLMs, as high scores on standard benchmarks may mask underlying reasoning deficiencies.